Okay, the third reading is essentially talking about the ideal gas law. And briefly, and you've seen this in chemistry, is essentially that PV equals nRT. And so if you keep the volume constant as you raise the temperature, the pressure goes up. Um, if you keep the pressure constant as you raise the temperature, the volume goes up. And so there are many different types of, you know, the relationships between the pressure, the volume, and the temperature. And they're related through basically how many moles of a gas that you particularly have. R is what's called the universal gas constant, as you know, which is 8.31 joules per mole Kelvin, or 0.0821 liters atmospheres per mole Kelvin. Frequently we'll use MKS units, and so it makes more sense to basically do joules mole Kelvin, because we're most considering in terms of energy. Liters atmospheres is also basically a type of energy, but we would tend to use joules per mole Kelvin. In chemistry, frequently you use liters atmospheres and per mole Kelvin. Now, the idea about ideal gas is that you have many, many molecules, and they're essentially non-interacting, meaning that they only interact with the walls of the container and not amongst each other. And so realistically, what you're really talking about in an atomic viewpoint is that you have individual atoms or molecules. And so frequently the other variety of looking at exactly the same equation is to do it in terms of the number of molecules that you have. And the idea being that if you end up doing that, what you're used to doing is you have essentially, the pressure times the volume is the number of moles of gas you have, the ideal gas constant, and the temperature. And the temperature actually has to be on the Kelvin scale. Okay, you don't do it in terms of degrees C. But the idea is the number of moles of gas are determined by, if you look at the number of molecules that you have, it's the number of moles, and for every mole, you essentially have Avogadro's number of atoms. And so Avogadro's number is 6.022 times 10 to the 23rd. And that's how many molecules that every mole has that many numbers of atoms or molecules. And so what you do is that that means that N is equal to Na. So it's PV, number of moles of gas, times Na, and that means that you have to divide by Na times the temperature. And so what you end up getting is the number of atoms or molecules that you have. You have Boltzmann's constant, which is just R over Na times the temperature. So this sometimes is just they're entirely equivalent ways of looking at it. Okay. Now, the idea being is that what we want to do is to get an idea about what exactly is causing the pressure in a gas. And mechanistically, because we're talking about mechanics, really what you're talking about is the atoms, because they only interact with the walls. As they hit the steel walls of the container, or the hard walls of the container, they tend to bounce off. And usually that collision is elastic. And so the idea is that if you have an atom or a molecule moving at some speed v, when it bounces off the wall, it doesn't stick to the wall, it actually bounces off the wall. And so it basically leaves with exactly the same velocity as it came up with. Now, if you looked at the change in momentum, the largest change in momentum is if it goes straight into the wall and straight back. And that will give you a total momentum transfer of twice times mv, if mv is the initial momentum. And what that means is that there's a force on the molecule during the time t, delta t, that it interacts with the wall. And so you can determine that force. And obviously if you have many, many, many atoms all bouncing off of the wall, that will create a pressure. And this force is what the interaction of the molecules with the walls, which causes the pressure. And so that force is just 2mv, the momentum change divided by the time of interaction on the walls. And so if you think about the containers having a distance d between the walls, what that means is on average it interacts with the wall on delta t of just, it goes a round trip time of a distance 2d divided by the velocity of the molecule. And so when you put all this in, is that the average force on the walls for a given atom which is bouncing off the walls is just mv squared over d. And in particular, now that if you, basically this is for every single atom, and so if you have n moles of gas, it's just Avogadro's number times n moles of gas. That gives you, basically increases it to a certain amount. And the idea being that only 1/3 of them at any given time is going, say, along the x direction, and another third along the y direction, and another third along the z direction. So only 1/3 of the atoms typically are going to interact with one of the walls. And so what you end up getting when you multiply this out is just Avogadro's number times n, the number of moles of gas you have, divided by 3 times mv squared over d. This is pretty easy calculation, right? And it's remarkable that it works as well as it does. And you can only have to go a little bit farther in that if you want to talk about the pressure, which is the force per area, then all you really have to do is, since you have d down here, the area, say if you have a cubical container, then the area is just d squared of one of the walls of the cube. And so that means that you have d cubed down here. And then the other issue is that in order to, and you still have this basically divide by 3, the only other issue is that you'd like to get something that looks pretty much like a kinetic energy. You have mv squared over 2, mv squared. If I divided it by 2, then I could get a kinetic energy, and so I have to multiply by 2. And so what you get is that the average kinetic energy of the particles, of a given single particle, you just have 2/3 and the number of moles of gas you have, Avogadro's number, divided by the size of the vessel. That size of the vessel is just v, and so the number of particles divided by v, and then you have the average kinetic energy. And so PV is equal to just 2/3 times the number of particles you have times the average kinetic energy. And so if you compare it with the ideal gas law for the number of particles, n Boltzmann constant k sub b times t, what you end up getting is that essentially k sub b times t is just essentially proportional to the kinetic energy. So since I have 2/3 here, I can basically get the 2/3 out front by multiplying by 3/2. And so 3/2 kT essentially is the average kinetic energy. And this is a really fundamental result, that the average kinetic energy of a particle is just 3/2 times kb times t. This is only considering translational kinetic energy. And so let's say a helium atom, which only has a single monotonic, it's a single atom, then you get 1/2 kT for every degree of freedom, and since you can move in all 3 dimensions, you end up getting 3/2 kT, and that gives you the total kinetic energy of, say, a monatomic atom. So this is extremely important, and so essentially what it relates to is that what causes the pressure, essentially, are the atoms bouncing against the walls, and in particular the kinetic energy of a given atom is just 3/2 kT. And so the total kinetic energy is just 3/2 times n times r times t, where n is the number of moles that you have. And so what it means is that the temperature is nothing more than a measure of the total amount of kinetic energy that's contained inside the gas. So now what we'll do is we'll do some practice problems talking about the ideal gas law.